When it comes to nuclear, we dig up uranium, use 1% of its energy, and bury the rest as waste for 100,000 years. It's a failure of imagination. This behind me is probably the world-leading example of a modular molten salt thorium reactor, and this could be a game changer for nuclear power. But to figure out how this works, I've flown out to Copenhagen to meet with Copenhagen Atomics just to see how they've had to make radical breakthroughs in new pumps to be able to pump 600-degree molten salt around without failing for 5 years, all the way to new lithium extraction technologies. Yes, there's lithium involved. That's an interesting one. And there's so much more. So in this episode, we're going to see just how this works and how amazing this could be. I'm Ricky, and this is Tuba Da Vinci. This video is brought to you by Mammoth. The biggest problem with nuclear power today isn't safety, it's economics. Traditional nuclear power plants are like medieval cathedrals, massive bespoke civil engineering projects that take a decade to build and go billions over budget. Copenhagen Atomics has taken a page out of Henry Ford's playbook. They don't want to build cathedrals, they want to build cars. Their design is a thorium molten salt reactor that fits entirely inside a standard 40-foot shipping container. The implications of this form factor are massive. Instead of building a reactor on a muddy construction site, they plan to manufacture them on a gigafactory on an assembly line. Their target? 1 reactor per day per line. By moving construction into a factory, you control quality, slash labor cost, and iterate instantly. If Reactor 50 has a minor flaw, Reactor 51 fixes it. Let's look at an estimate of what that does to the price tag. A traditional Gen 3 plus nuclear reactor costs anywhere from $6,000 to $15,000 per kilowatt of electricity capacity. That's why the Vogtle plant in Georgia costs over $30 billion. But target costs for a factory-built modular reactor are around $50 million for a 100 megawatt unit. If we assume a thermal to electric conversion efficiency of 40% using modern supercritical CO2 turbines, that gives us a 40 megawatt electric output. This is a disruption of the energy market on the scale of the transition from horse-drawn carriages to automobiles. Molten salt reactors aren't new. We built them in the 1960s. In fact, we made an in-depth video a few weeks ago about a thorium molten salt reactor, which we'll link below. But CA has radically changed the internal geometry. They patented their design as the onion core. Most molten salt reactors use graphite to slow down neutrons. But graphite degrades under radiation and becomes radioactive waste. CA uses heavy water, D2O, instead.
If we zoom into the core, and this up here is like a very early prototype, just made to run with water. Call it an onion core, but it's several concentric layers of fuel moderator and a blanket salt.
The onion design arranges the reactor in concentric bloated cylinders that look pretty much like an onion when cut in half. The center is an unpressurized heavy water moderator. The middle, the fuel salt, thorium plus uranium. The outside, a blanket of thorium salt to catch leaking neutrons and breed new fuel.
The reason for this choice of this design is this sphere. That means that we make the reactor really, really efficient. Because neutrons, when they are born, they go in all directions, right? So to make a perfect reactor, sort of in terms of efficiency, we want to make a sphere. And that makes the reactor crazy efficient. That's why we can make a breeder reactor and not just a burner reactor.
Coming on site combined with our research beforehand really helps us bring these stories to life. And when it comes to research, there's a new tool that's really been helping out our team. This is Mammoth. And instead of paying $20 a month for Gemini, ChatGPT, and Claude, Mammoth is a platform that gives you access to all the best models in one place. Mammoth breaks out the best models for various tasks based on text, image, research, or reasoning. Their interface is clean and familiar, but check this out. When I was researching for this script, I used Perplexity, but I can easily re-prompt my request and pick a new model, like Claude Opus 4.6 that just came out. For images, Nano Banana is really good, but I can easily compare to others like Stable Diffusion with the same prompt. Create custom Mammoths with unique system prompts for the things you do most. I have a Mammoth for custom system prompts for research, and another for designing thumbnails. You're probably familiar with user prompts, the part we type in chat. It's the what. But the system prompt is the why and how. It tells the AI how to act and think, like be my lead researcher or you're my chief software architect. And if you like command line tools, there's Mammoth Code. It installs just like Codex or Cloud Code right in your terminal. And they offer API keys if you're building an app or use services that need API keys. So however you use AI, level up your game, bring the power of all the latest and greatest models in one place using Mammoth AI. Learn more and get started today using our links in the description. Huge thanks to Mammoth and you. Now back to the show.
Here you have essentially something that is below 100 degrees Here you have 600-700 degrees, below 100, and 600 degrees in the blanket salt.
This creates a massive engineering challenge. You have heavy water, which must stay below 100 degrees Celsius, sitting just 10 meters away from molten salt at 700 degrees Celsius. The patent covers the specific vacuum insulated barriers and thermal insulators that make this thermal separation possible. If that heat crosses the barrier, the water boils and the reactor shuts down.
The reactor is a molten salt reactor, so it has a liquid fuel, molten salt, and it's a fluoride salt that we operate from 600 to 700 degrees. But this salt, in order to go critical, we use a moderator, and for this we use heavy water. And heavy water has several advantages. The primary is that it has a very good neutron economy, and that basically means that it's very good at slowing down neutrons and not eating any of those neutrons, so that they can lead to fission in the uranium or capture in thorium to produce new uranium for the reactor. And the other advantage is that since it's a liquid, it doesn't really suffer any degradation from the radiation of the reactor, because inside the reactor there's very high levels of radiation. So any solids material will slowly degrade over time and need to be replaced. But with a liquid, we can actually maintain it and keep it indefinitely. And we then also have thermal insulation made of graphite felt in between the salt vessels and the water vessels to keep them cool. There is basically a bit more than an inch of insulation in between. But then,
does that ever need replacement or anything?
Yeah, so whenever we replace the whole reactor vessel, the core goes as well. So all the vessels that are in the core and the insulation and sensors and pumps, all that gets scrapped and gets recycled. But the salt and the heavy water gets reused.
Now, besides molten salt nuclear reactors, we've actually covered other applications of molten salt for energy generation. Remember that billion-dollar solar thermal plant that failed a couple years ago? That used mirrors to concentrate solar energy and store it in hot molten salt. But the plant had so many technical challenges, from corrosion to leaks and all sorts of problems, that it eventually shuttered. Make sure to check out that video. We'll have links down below. But ultimately, what we found when making these kinds of videos is that working with molten salt is really hard.
So we started by developing these molten salt loops. Back here we have a furnace with electrical heating. We have a tank with salt, and then we circulate the salt. And this is a test platform where we have filters, valves, pressure sensors, flow meters, all the things you need to build a reactor. We test that here and do optimizations. We reconfigure them, and then once completed, we put them into the testing area next door here. So they are just running day and night, year round. The gloves are so that we can do, if you need to adjust something, you can just put your hands in there and do the adjustment and then keep it running.
So that's molten salt at temperature,
Pumping around just like you would do in a reactor. And it's for test and validation of all our technologies.
600 degrees sounds very challenging. How do you withstand that kind of temperature safely for... You mentioned some of these have been running for a year nonstop.
Yeah, they're running for several years nonstop. Everything here is made from stainless steel 316L, and 316L is absolutely adequate for these temperatures. And people always wonder about corrosion from molten salts. But if you have a purified molten salt, it's absolutely non-corrosive. It's the impurities that makes it corrosive. So rather than use expensive alloys, we have chosen to develop engineering controls where we keep the salt clean at all times. And then the corrosion is sort of like vanishingly low, a few microns per year. So corrosion is not really something we bother about anymore.
In any fluid system, the pump is usually the main point of failure. In a nuclear reactor, you can't just send a guy with a wrench to fix a leaky seal. The pump is radioactive. This is often the Achilles heel of molten salt designs. Now, this is where things get amazing, because Copenhagen Atomics claims that they've solved this problem by developing and patenting a canned rotodynamic pump, which is an absolute engineering marvel. And here's why this patent here is worth millions. It handles the extreme heat of the salt running at 700 degrees C.
To develop the technology before going to a commercial reactor, we needed pumps, and there wasn't any pumps that are commercially available for our type of environment, which is 600 to 700 degrees. And so that posed, of course, a bunch of different challenges. And so we have basically decided to develop our own pump. We first developed this pump over here, which is a can pump, but it happens so that we can not use permanent magnets, but we can use ferromagnetic material like iron, and we can use copper at these temperatures. It's just below the Curie temperature where iron demagnetizes, but these temperatures it still works. We basically invented a way to then insulate the windings and use low voltage and high currents. And then the other part of this pump is that it uses hydrodynamic bearings. So it basically doesn't have a ball bearing with the rolling elements, but we're also developing another type of pump that's called AMB, or active magnetic bearing pump, where we have the same stator design and the same pump volute design, but we then have additional coils here. The hydrodynamic bearings are like a wearing surfaces, so while they do tend to last very long, they can degrade over time. So instead here, we're using these electromagnetic coils to levitate the rotor. And that means that the whole rotor assembly is levitating in the salt, and all the coils are still cooled by the salt. But now we don't have any mechanical touching surface. So the longevity of a pump like this can be much longer and operate for 5 years at a time in a reactor without needing any maintenance.
This part is critical because the reactor is a black box. Once it's turned on, you don't want to open it and have to deal with spent fuel. But let's address the elephant in the room. Even if it's cheap and efficient, people are going to ask, do I really want a nuclear reactor in a shipping container sitting in my industrial park? And the answer is yes. No, I don't think anyone would say yes. But CA's answer to this is something they call the cocoon. The reactor container doesn't just sit out in the open. It slides into a massive solid steel bunker that weighs 1,000 tons. This cocoon has steel walls that are 20 inches thick. The purpose of this beast is threefold. One, external protection. I was kind of worried about this too. What if an airplane crashes into a factory, like just a total accident, not even an intentional attack? What if a missile hits it, right? The cocoon is designed to deal with this. You could drop a 747 on it and the reactor inside would likely remain intact. It also acts as a massive shield, keeping all radiation safely contained so workers can work around the facility without protective gear.
So you have to actively pump the fuel salt and the blanket salt into the reactor core in order for it to go critical. And that's what we mean by passive safety, because if you cut power to the pump, gravity will drain the salt back into the storage tank, and you wait for the power to come back, and then you can start producing energy again.
But what exactly is this wonder fuel, and why do we think it could be even better than fusion? We've done a deep dive on thorium before, which you should definitely check out if you haven't seen this one before for the entire physics breakdown. But here's the engineer's TLDR on why this fuel is a game changer. Current reactors use uranium-235. It's rare, only 0.7% of natural uranium. It's expensive to enrich and produces waste that stays radioactive for tens of hundreds of thousands of years. Copenhagen Atomics plans to use the thorium breeder cycle. It's abundant and already mined. Thorium is a byproduct of rare earth mining. It's 1,000 times more abundant than U-235. It's literally dirt cheap. Raw thorium fuel is about 80 times cheaper per kilogram than uranium, costing just $60 per kilogram versus over $4,500 for enriched uranium. Now here's the killer feature. The final commercial reactor is designed to start with a Kickstarter of transuranic waste. Current nuclear waste needs to be stored for 100,000 years. CA reactor waste and the fusion products from processed nuclear waste need storage for only 300 years. Now this seems like a lot, but we have buildings over 300 years old. This is a manageable engineering problem, not an existential civilizational threat. Compare that to having a high dangerous waste for 100,000 years. How do you even label the site so that generations millennia from now don't accidentally think that they came across an interesting archaeological site only to die from radiation poisoning or cancer?
What does the spent fuel look like in your reactor?
When we run the reactor and it reaches equilibrium after 10, 20 years, basically the fuel salt doesn't change whether you run it for 50 or 100 years. So if you ever wanted to dispose of this fuel and you say, we don't want to use molten salt reactors anymore, it's been 500 years and now we have something better, then you could start to slowly burn the fissile material without adding new fertile material, so without producing new uranium, and just slowly burn all the fissile material you have while still removing fission products. And because you do this very efficient process where you remove the fission products, you could burn a fleet of 100,000 reactors down to a few hundred reactors and only need to dispose of the waste of those few hundred reactors. But this is a problem for several hundred years in the future. So, potentially there's other solutions as well.
Yeah.
But the question we always ask in these videos is, if this is so great, why aren't we doing it? What has kept the industry from going down the thorium route over the past 70 years? Beyond the hot molten salt loop we already talked about, this brings up the most complex physics challenge Copenhagen Atomics had to solve. It's not the thorium, it's the salt. Well, it's actually the lithium in the salt, to be precise.
Our reactor uses uranium and thorium, and we use those as fluorides, so uranium tetrafluoride and thorium tetrafluoride. Both of those have melting points above 1,000 degrees Celsius, and we don't have materials to build a reactor that runs 1,000 degrees Celsius, so we need to lower the melting point to have the salts be liquid. And so for that, you can mix it with other things that lowers the melting point, similar to how alcohol will lower the melting point of water if you mix them together. So we create a eutectic of uranium and thorium separately with lithium fluoride to lower the melting point, and that lowers the melting point for uranium to 490 degrees Celsius and for thorium to 550 degrees Celsius. And so that means that when you go to 600 degrees, those are both liquid and are well above their melting points, and you can pump them around.
So what happens to lithium-7?
So when we take the natural lithium and we separate it, we have our own process to doing the enrichment on the lithium. We take that and turn it into a fluoride, and we mix it with uranium, and then we have our base salt that we can pump around. And when the lithium is in the reactor, it's basically very unlikely to interact with the neutrons. So it just sits there acting as something that lowers the melting point as a diluent, but it doesn't do anything. It doesn't contribute to the chain reaction. It has very slight moderation effects, almost nothing. So it doesn't degrade. So it just stays there. And when we've used the salt and put in a new reactor, we can reuse that salt, and that same lithium will go into the next reactor and the next one after that, and it just stays there.
Remember, this reactor pumps the nuclear fuel dissolved in molten lithium fluoride salt. The lithium carries the fuel, but natural lithium is a mixture of lithium-7 and lithium-6. So what gives? Well, it turns out that lithium-6 is a neutron poison. To understand why this is, you have to understand how the thorium fuel cycle works. In a normal reactor, you have uranium or plutonium as fuel. You hit them with a neutron, and they break up, releasing on average 2.5 neutrons. You need one of these neutrons to break up another atom to keep the reaction going, but you have to capture the rest in control rods to avoid a runaway chain reaction and a nuclear meltdown. But with thorium, things are different. Thorium itself isn't fissile. When you hit it with a neutron, it turns into uranium-233, which is not only fissile, but much more energy efficient than uranium-235. That's the actual fuel that generates the power and the 2.5 neutrons. So in this case, you need one neutron to split uranium-233 and generate power, and one spare neutron to breed more uranium from the thorium fuel. If you have lithium-6 around, it'll suck up all the spare neutrons and kill the reaction like tossing water over a campfire. But lithium-7 is completely transparent to neutrons. It's 20,000 times less likely to absorb a neutron than lithium-6.
So how important is it to separate the lithium-6 and 7? If let's say if you didn't do that, would it still work? It would just be less ideal?
The reactor wouldn't even go critical, and you would need like much higher enrichment in order for our reactor geometry to go critical. And you could use other materials to lower the melting point, but then you wouldn't be able to breed in thermal spectrum. So it's sort of a choice between, do you want a reactor that just burns uranium like light water reactors and uses other more readily available salts, or do you want to be able to breed and use lithium-7? And this isotopic separation of lithium is much easier than uranium. So with uranium hexafluoride, there's basically 100th mass difference between uranium-35 and 38 hexafluoride, where for lithium, it's lithium-6 and 7, so it's 1/7 mass difference. So it's a much bigger mass difference, so it's a lot simpler process and doesn't require as much energy to do the separation. And so we need to enrich the natural occurring lithium to be very high abundance in lithium-7. So natural lithium is roughly 5% lithium-6, and we need to be below 0.01% lithium-6.
But here's the problem. The only known processes to get that grade of lithium-7 are lab scale and produce a few grams at most. But you need 3 tons of salt per reactor. How on earth do you manage that? Well, this gets to what really is at the heart of the breakthrough. Copenhagen Atomics decided to invent a new way to refine lithium. They don't talk too much about it on their website or investor decks because, well, that patent is still pending. But we did find the patent application. It's kind of like a still to get moonshine, only it's to get super pure lithium. Here's how it works. They use a vacuum chamber with a heated bottom plate, evaporator, and a cooled top plate, the condenser. Instead of complex pumps or gravity feeds that require precise leveling, they use capillary members to transport the molten lithium. The lithium-6 is lighter, so it evaporates slightly faster. It condenses on the top plate and flows backward via the wicks, while the heavier lithium-7 stays on the bottom and flows forward. By stacking hundreds of these stages in a single unit, they can separate the isotopes without using a single drop of mercury. And the best part, it's a continuous flow system. When I started the research for this video, I didn't really realize that a lithium extraction process would be at the heart of what makes it so possible. But here we are, because modular reactors have been around for a while. Some of these things have been done before, but this might be that thing that we always ask, why isn't it everywhere? It might be this, and they might have just figured out how to do it. But here's where the story gets interesting beyond the engineering. Copenhagen Atomics plans to operate on a nuclear energy as a service model. They're not selling the reactors. They'll own the reactors. They'll own the liability. They'll own the fuel and the fuel supply chain. They simply sell heat produced locally. Their target customer isn't necessarily the grid. It's heavy industry. I'm talking aluminum smelting, ammonia production, and hydrogen generation. This could open a new era for red hydrogen, aka nuclear hydrogen. Since the age of nuclear, we've seen other technologies like airplanes advance so far, and that's because we've had a chance to iterate plane by plane. But with nuclear, we've seen plants that are 30, 40 years old, and just when we've had new breakthroughs and new ideas, we've seen people turn their back to nuclear. And some of the reasons why we've seen that happen can be addressed and solved with something like this. This is portable and modular. This is built in a factory and assembled on site. And it's inherently safer because if you drain the water out, you could completely stop the reaction. And what I love most about this is the nuclear component. What you do with this high heated molten salt is up to you. You can run steam turbines, produce electricity. You can power district heating areas with this. What happens from here is kind of up to you. But what if we did want to use this for electricity? So for a single building, this would be overkill. But how about for data centers? For an AI training cluster that needs 40 to 50 megawatts of flat, reliable power 24/7, this could be the holy grail. You drop 2 containers in the parking lot, one for redundancy, and you're off the grid. And the best part, you're looking at lower energy costs than solar with targets of $20 to $30 per megawatt hour. We could do some quick back of the napkin calculations, but it turns out that one shipping container reactor could power roughly 465 large office buildings. This takes what's been historically really hard with nuclear and removes a lot of those overheads, right? The regulatory approvals, massive building structures, and everything else. And by being a thorium breeder reactor, you can actually make your own fuel and completely control and be better with utilization of resources. There's so much love about this tech. But what do you think? How big of a game changer could this be? Could this be what we need to see a renaissance of nuclear power? Sound off in the comments below. And until next week, I'm Rick Da Vinci. Thank you so much for watching.